Hello, so today we'll be studying, at least reviewing, how scheduling works on a real system. And for that, we are going to use, as I've given you in the second exercise, two processes, two totally interactive processes, and one computation process. Okay, so let me just write it down. And the goal is to see how this really works. First, obviously, on this example, and then we're going to relax some of the assumptions here, at least how these processes work, in order to see really what happens on your own system. So to see that, obviously you've got like the constraint, the main concern of A and B, since they are interactive, is response time. Whereas for C, it's what matters most is having the access to the CPU. So CPU access, that's the main concern of C, having as much as possible the access to the CPU. As for A and B, obviously it's the response time. So whenever you ask for something, A and B ask for something, and they get it. Once they get it, they would like to have right away access to the CPU in order to do whatever they have to do, and then probably go back to sleep, be blocked, waiting for another input or something like that. So how is that? Since we have if you've got something that has, once a small response time, a very quick response time, and not just probably, the only algorithm that is possibly that we could use in order to give the impression that all processes are running at the same time on the limited resources we have is to use a round robin. Okay, no matter what the quantum is. Okay, we'll come back to this point later on, but you've got to use a round robin. As for C, the computation process, it doesn't care about response time. It cares about access, CPU access, having as much as possible the CPU for its computations, for its all the operations that it wants to do. So basically, a first come first served is better suited for such an application, a process. So knowing that, so that means that from now on, if you want to schedule, if that is my timeline, okay, just to show what happens, okay, instead of having one ready queue, we are going to have two ready queues, one per type of process. One ready queue for the interactive processes, that uses a round robin policy, and the other one for the non-interactive, for the computation processes, that uses a first come first served policy. Now when we start off running, let's say that obviously in the exercise, I think I've said that C comes first, then A, then B. Now when you start running these processes, the question that comes to mind first is, where should we add these three processes, to which queue? Okay, so because the system doesn't know that C is a computation process, that A is an interactive process, because when you run your own processes, you never tell the system. So the system has to figure out that on its own. So one way to do that is to say, okay, since I don't know if they are interactive or non-interactive, what matters most to me as a human is the response time, since that is what matters most to me, to make sure that I don't see that one process is not running smoothly. So that's why, since I don't know the nature of C, A, and B, I'm going to start by, saying that probably C, A, and B are interactive processes. So that might be a mistake, and we know it's going to be a mistake in the case of C, but the system doesn't know that. So as a precaution, it's gonna put that as an interactive process. Why is that? Because it cares about response time. So what it's gonna do is, first, obviously, if we schedule things the way we've done it till now, is that C is gonna run first. It's gonna be chosen, so you remove it from here. It runs first, and then at some point the system, obviously this is a round robin, so it's gonna use, since the computation process, it's gonna use the whole quantum. Now the system is gonna say, okay, my heuristic is that if it has used its whole quantum, that means that it's not interactive. Okay, because if it were interactive, it would have done like a little bit of CPU instructions, run CPU instructions, and then right away ask for input, which was not the case. So that's why. So C is going to, the system is going to push it back on this queue. So the way the system works is that it's going to see if you are using lots of CPU time, then you're not interactive. If you're using less, then you're more interactive. Okay, so in our case, obviously it's binary. It's either interactive or non-interactive. We'll see that later, how to relax that and have like multiple, graduations, different levels of interactivity. But for now, we've got like either interactive or not interactive. So C, okay, has stopped. Now A runs. Since it's interactive, we know that A runs for, a little bit and then stops, asks for input. Okay, so it's not going to use the full quantum. So the system says, okay, this one is definitely interactive. At least I think it's interactive. Same thing goes for B. B runs and doesn't use the whole quantum, and that's great. Now let's assume that they're still waiting, as if like A and B. A is your text editor and B is your browser, so it's not a game. So you're waiting. You're not really giving the input as a user, so the processes are blocked. So in the meantime, C, obviously, since the system, in the first queue, the round robin queue, there are no processes left, then the system is going to choose processes from the second queue. Now, one thing I didn't say is that since you have like two different queues or many different queues, obviously you have to apply some kind of priority. Okay, between the queues. Okay, because when we had like A and B and C on two different queues, then obviously we had to choose one process, and we chose A and then B. That's because A and B are on the interactive queue, which is more important to us as humans, as users, okay, of these types of operating systems. So that means that we gave a higher priority to the round robin queue than for the first come first served, which makes sense. So because we want to minimize response time. So now that C, let's say C runs now, because it's the only one on the queue. So C runs, and let's say that C runs for a long time. And at some point, A gets its input. And let's say that B gets it too. That one is for B. Okay, let's see the response time, what the system has to do, the scheduler has to do. For this to work, obviously the scheduler has to stop C right away. So it's going to stop C, and since C has ran for a long time, it knows that it's a non-interactive process, so it pushes it back on this queue, on the second queue. And then it chooses, obviously A is back and B is back, and since they didn't use before the full quantum, then they are interactive. The system thinks they are interactive and pushes them back on the first queue. Now the A is chosen, A runs, and then for a little time, Okay, so it's still interactive. And so as you can see, the response time for A is this. The response time for A, oh, come on. Okay, the response time for A is this. So it's definitely, it's like, it's very small. So obviously if it's like the quantum is 50 milliseconds and then this is like 1 millisecond or 2 milliseconds or 5 milliseconds, still for a human, it cannot, you know, this is not visible. So the system, as if like this is instantaneous to us humans. So this really works. What about B? B also runs, is chosen, and runs, okay, for a small amount of time. And as you can see, the waiting time, the response time, sorry, for B is this. So it's too small. It's small, and this is what makes it work. This is what makes the system work. So because if every time you got an interactive process that comes into the queue, it has a higher priority than all other processes. The other processes are going to be stopped, interrupted, preempted by the scheduler, and so the response time is going to be, okay, good enough for us. Obviously, if you've got like 50 processes in here, okay, obviously the last one or the last ones are going to suffer from waiting. Okay, so the response time is not going to be that good, but that means that your system is saturated. Okay, so you've got like, it's overloaded with processes. Okay, that said, if you think about your systems, you never run multiple interactive processes at the same time. You can run them, but if you run your browser, your text editor, whatever, you know, the one you're not using, the ones you're not using, even if you've ran 10 interactive processes, the ones you are not using are going to be blocked. And there is one that you would be using at a time, probably. Okay? Or going back and forth between your text editor and maybe your graphical interface. Okay, so when you do that, obviously if you schedule that the way I'm doing it here, you will see that the response time is always going to be, the number of active ready processes is going to be so limited that the response time is always going to be good. And that's why things work on your systems. Now on real systems, you don't have just like two queues, you have like multiple levels, not just, it's not either interactive or non-interactive. It could have like multiple levels of interactivity, and that's why you've got like a, wow, levels, okay, with round robin on the highest level with a very, 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 very small quantum, and on the second level lesser priority but with a, you know, bigger, larger quantum, and so on, so forth, until you get to the last level, which has a round robin, basically, okay, with a very, 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 very large quantum, which is like almost similar to a first come, first served policy. Okay, on real systems, you could have like 100 of these. Okay, and the system works the way I've described it before, and this is what happens on your systems, and that's why your systems are efficient, and your operating systems that you use, the Windows, the Linux, since all these operating systems, they do this the same way. Obviously not necessarily using the same heuristics for to choose to say who is going to be interactive, non-interactive, but they do it the same way. Now let me just add one more thing, one last thing about this. What if at some point C becomes interactive? So let's say that C now runs, it's the only one, and it runs and becomes interactive, so it doesn't use lots of time, CPU time, and so the system is going to say, okay, it didn't use lots of time, so that means that maybe it's becoming interactive. So instead of pushing it back, so it is asking for input output, obviously, so when it is going to come back, the system is going to push it back and to put it back here. And that means that if it really became interactive, then response time is going to be good. But the way we've shown that with A and B before, okay? Now, same thing happens with A and B. What if A and B now run and they use the whole quantum? So they are becoming less interactive. So same thing happens if A and B, if that happens to A and B, then they are added after they, finish using the quantum, they are added to the second queue. Okay, and that way you have like this back and forth, exchange between the queues of the different processes depending on how they are executing. Okay, and this is what we call a multi-level feedback queues. The multi-level feedback queues. The multi-level, obviously, you've got many levels of queues, all the levels of queues, 100 levels of queues or whatever. And the feedback is because the queues exchange, okay, one process goes from this queue to this queue, from this queue to this queue, all the other way around, okay? So that's why we call them multi-level feedback queues. The last thing to say is that when you use a priority-based algorithm, okay, obviously in this case just with 2 levels, in this case with 100 levels, what could happen is that the processes on this one here on the second level with the lower priority could end up not being able to use the CPU. So this is called starvation. So any priority-based algorithms suffer from starvation. So if every time you get like many processes that have a higher priority that come in, okay, they are going to reduce the chances of the processes on the second queue or the lower priority queues to run. So in order to handle this, to handle the starvation problem, that means that these processes cannot use the CPU. They are starving for the CPU. One way of doing that, the solution is what we call is aging. Solution, it's called aging. Okay, so that means what? That means that, okay, if you wait for a certain amount of time, okay, the system is going to upgrade your priority. Is going to give you a higher priority. It's going to make you like a VIP process. Okay, so you're going to move on from one level to another until you get to the highest level, and that way you are going to at some point, even if you're going to wait, you're going to wait obviously because you have a lower priority than other processes. At some point definitely you are going to use the CPU. You're going to be able to use the CPU, and that's how we deal with starvation. So because we have priorities between queues, that is going to probably, potentially, it's not necessarily, it's potentially lead to starvation. And in order to deal with starvation and to handle this problem, the idea is to age the processes. Aging the processes is, hiring, upping their priorities, okay, after a certain amount of time, a certain amount of waiting time, okay, so this is how the system works. Okay, hopefully you've understood how this works, and please do this exercise, at least try to do it on your own, follow my logic, and then prepare your questions if you still don't understand something. Okay, good luck. Bye-bye.